So, hi everyone. We're here to talk about this nice, long, wordy title, Drinking from the Fire Hose with Duct-tape-free reactive Java applications. That's a whole math load worth of stuff. We will actually touch on what we mean by duct tape and what we mean by fire hose as we go through. But this is an alternate, probably cleaner name for the talk that will actually bring in and touch about the different things. We're going to talk about combining in-memory data grids with hiccup-free Java to actually get things to work better or to do things we couldn't do before. And in that, the highlights are in-memory data grids and hiccup-free Java. We'll cover those in the talk. From an agenda point of view, we're going to talk about those three things. We'll talk about how they come together in some actual practical examples, and we'll cover some use cases of applications in the real world that we kind of sanitized from their actual real customer situations, but these are real applications with real uses of data grids with clean in-memory Java. We'll introduce ourselves. I'll start with me. I'm Gil Tene. I'm the CTO of Azul Systems. At Azul, we make Java virtual machines. We make what we believe are the best Java virtual machines on Earth. And one of the key things that we've done is basically solve garbage collection. I've been working on garbage collection for over a decade now. Wow, it's 13 years now. And this is some evidence of me actually working on garbage collection. How many here recognize what the contraption is? That's a trash compactor. It actually compacts garbage. It's a very important function in garbage collection. In my house, the purpose of a trash compactor is to delay the full GCs to the weekend. So I pick up the trash and go to the trash can only once a week, and that takes the pause away or the annoyance. In this case, the trash compactor was broken. It wasn't working right. Fragments were coming out the back. The defrag function wasn't working right, so I had to fix it. And I thought it'd be funny to actually take a picture with the book. But the main message in this picture is it was taken in 2004. So I've been thinking this is funny for 11 years. I really need a new picture. I've built all kinds of things, worked on virtual machines, obviously, physical machines, helped design instruction sets, and worked on operating systems and firewalls and networks. I'm old. I also like to go around depressing people about how they measure latency. If you've looked at any of my material online, I have lots of talks and workshops about common mistakes and issues in latency measurements and maybe things you could do to work around them. But that's not the subject for today. Hand it over to John.
All right, and so then my name is John Kaczala. I'm a senior Jboss solution architect. I'm based out of Dallas at Red Hat. I've been with Red Hat a little bit, about 3.5 years now. Interesting thing about me is I was a customer and was so impressed with the middleware portfolio and Jboss that I wanted to come on and work for the company. So my background, I'm actually out of the telecommunications industry, so I've worked building many large solutions for a lot of the major network equipment providers, Ericsson, Alcatel, Nokia, what have you. I did a lot of work on databases and sort of the real-time databases. I don't know if you guys are familiar with the wireless network at all. Something called a home location register was sort of a pet project of mine. So it's really kind of become this big data and in-memory. So I'm kind of a really big enthusiast there. Having come on to Red Hat, I've worked in a whole bunch of other accounts outside of telecom. So I wanted to get some exposure to other different vertical industries and kind of be able to crossbreed some of the things that folks are doing in telecom and wireless and bring them into places like retail, oil and gas, what have you. So I've been working with direct customers, and I've recently switched. Now I'm going to be working with our channel and partner organization. So having done a lot of work with customers, I often feel that when I'm talking to them about data and really how to build a proper architecture, I feel a lot like this guy. So I'm always trying to give them this mind share, this mind thought to really figure out really what's the best approach. So that's how I feel, and we'll see how it goes from there.
Yeah, I think we might all start feeling like that every once in a while when we have to explain stuff. Oh, you got to understand the system and how it feels. Yeah.
Yep.
So we talked about this duct tape thing. So to explain what we mean by duct tape engineering is actually a great thing. I think every engineer should experience and use duct tape in one form or another, either physical or virtual. Anybody know what this picture is from? This is probably the best example I know of successful duct tape engineering. Truly heroic successful. Yeah, that's the Apollo 13. Take a square peg, put it in a round hole with duct tape from millions of miles away. And it worked. And it's great. And this shows you the power of duct tape engineering. But right along with it, duct tape engineering should be the thing you do when you need heroics, not the thing you design with normally. And when you're applying a lot of duct tape to work around problems, that's usually a sign, a symptom of architecture that has a problem, or that there's a fundamental thing that you're working around, that if just that thing was solved, no duct tape would be needed, things would be more reliable, simple, and you wouldn't need heroics. If the hole was the right shape, the filters were actually meant to work with each other, that would have been better. We have plenty of examples of duct tape engineering in Java, and we're going to talk about a couple of them here. The first one is working around the JVM and heap size limitations in Java that are practical. In reality, JVMs work great. They're amazing pieces of engineering, but they have their limitations from practical use. And one of the big limitations is we can only really use a certain amount of heap before it gets so painful we won't do it. It's not going to work, but we don't like going to lunch to wait for a result. So as a result, we tend to keep our things small. And the kind of things we do to work around the limitations of heap size in Java, or the practical limitations, are breaking applications into lots of little pieces, even though they run in one computer. We do things like avoiding allocation or reducing allocation with object pooling and interesting architectures, trying to avoid mid-size objects, imagining that the whole world is either die young or stay on forever, and thinking that anything else like a cache is non-existent. Or trying to design it away from the JVM by taking it off heap, out of process, move it out of my memory because it's too painful to have here. Those are good examples of duct tape engineering, very good, successful duct tape engineering projects that you see around the Java world all the time, like moving off heap, because JVMs have strong limitations and we do want to process a lot of data. We'll touch back on an alternative to duct tape in a little bit later. A different form of duct tape engineering is building your own stuff, even though there might be some better systemic way to do it. And one of the most common places I see that is it happens around how people manage their data in an application that has multiple instances. Now, this is sort of an evolved field. There are multiple alternatives today, but a lot of people will still start off with their own little homegrown hash map or cache or something that they rolled in their own process. Then when they grow into multiprocessor or load balanced or other things, they'll start figuring out how to have multiple of those. They start being inconsistent and then create replication and availability and whatnots on top of them. And often we see a lot of roll your own there, a lot of duct tape. Because all you need is a tiny little bit, a tiny little bit, a tiny little bit. I just need that feature. I already have something working. Let's add it. Often you step back and you say, well, instead of building a lot of duct tape, I could just use a working system that already takes care of all those things for me and basically refactor away a lot of the complexity. Both of those examples we'll deal with today. And if we're going to look at the parts, as we said, it's in-memory, Datagrids, and Hiccup-free Java. We'll start with the in-memory and Datagrid parts.
Yeah, so going back to how this comes together, looking at a properly architected solution for events, things that are basically capturing high-speed information elements that you want to start basically collecting. That's where this interest in Datagrids comes in. So just to kind of understand what we mean by a data grid, right? So a data grid is really an architecture and a set of services. And so it's really a loose coupling to factor out how to actually handle and how to arrange memory from sort of your application, right? So it's sort of a loosely coupled multi-tier architecture. One of the key things is it has a common set of access mechanisms, right? So you can kind of think of it as an API. So what that means is you write your application toward the API, and it's independent of actually the decisions that you want to make at deployment. So going back to what Gil was talking about, where if I roll my own things, oftentimes I'm tightly coupling a deployment model with an implementation in my application. The beauty of sort of a data grid model is that I've kept them loosely coupled. I can focus on my application, just match to the well-defined interface of my API, and then at deployment, I can change characteristics of my application. So, really, once I take the data grid concept as an architectural premise, that allows me to deploy my application in a different, multiple different ways in terms of consistency, availability, replication, where data may be located, how I want to partition the data, all these types of things. I haven't sort of hard-coded it into my application. It's really a deployment decision. So it really gives you a lot of control over the topology that you're going to have, but you're not designing that hard-coded into your core application. So to kind of understand how this comes about, the interesting thing is to look at the different ways that I can deploy a data grid. So if we start from the very simple, and this is just a small step from the way you would typically build an application, this is where I'm managing a portion of my data cache within the context of my application. I've just basically loosely coupled it. I'm using an API. So it's a very simple, very embedded approach. So every model you look at is going to have different trade-offs in terms of characteristics, right? So, if you look at this model, it's very simple. There's not a lot of complexity to it. It probably doesn't scale very well. But I do have that loose coupling, and I do have the ability to change my deployment architecture if I want to. If we go on and look at another architecture that we can deploy, this would be something in terms of a replicated cache, right? So the idea with a replicated cache is I'm moving multiple copies, and I'm pushing them and keeping them close to perhaps the point of consumption, so that if I have, say, high volume reads, this is an excellent architecture, right, to really cut down on latency, to also provide you, say, redundancy because I have multiple copies now. I also have, geographic failure capabilities because I can maybe spread these things around location-wise, what have you. So this is really a first step to building an architecture that starts to embody a lot of the characteristics that we would need from a more real-time, scalable type of application. And then if we look at, finally, the sort of the ultimate of really how to scale to really, really large volumes, that's where we look at a separate data grid tier. So, if you kind of understand this idea of a data grid, right, it's an in-memory cache, and, is what Gil was saying, as we have to strike this balance between, how much memory do we actually want being managed by a machine, and how many copies or how many shards, if you will. So, I can do things like sharding, where if the volume of my data grows beyond, say, just the core capability of the address space of a machine, I can use the algorithms in the data grid to partition my data into multiple instances across these shards, and then I can basically build redundancy, high availability in terms of how I'm doing the sharding. So, as we look at what people are doing with a lot of these in-memory type solutions, you want to store information that is maybe highly high volume, but that maybe doesn't have a long life duration, right? So if we look at the IoT concepts and things that we maybe want to collecting with IoT, and we'll get into a little bit of those types of applications, but this is sort of an excellent architecture to drive that capability. So, like I said, there's always design trade-offs in terms of what's the best way to deploy it, right? There isn't one answer that solves every problem. So if we look at really the different scenarios that we talked about, if we want to look at the embedded model, right, that's the very simple data grid, the replicated concept where I have, say, multiple copies, and then more or less the full data grid tier, that's where I can start sharding across multiple machine instances. If we look at the characteristics of responsiveness, so in the embedded model, from a responsiveness characteristic, only the synchronous writes are occurring any type of cross-process latency, right? So I really have a very tightly coupled system in terms of having this responsiveness. Now, if I start looking at a replicated model, right? So this starts to imply that it's sort of off machine into somewhere else. Now, that's where I start seeing that all operations start to incur some type of penalty, right? Because now everything is more or less off board, off machine. And then same thing too with the sharded model, right? So if I really want a really fast process, the embedded is a great model. But then, it does have its limitations because I can't infinitely scale it up, where if I go to a sharded model, that can scale. So that's really the next point here. So from a data size limit, in my embedded model, I really can only manage about as much memory as I can have on that one machine or that one process. Same thing too from the replicated model, right? Because replicated means that I'm taking that exact copy and just doing that over several machines. So it really sort of has the same limitation as embedded. But then, that's really where the sharded model comes into play, right? Because now I sort of have this unlimited capability. So if we look then at this idea of data and application coupling, right? So we're going to see that in the embedded model, that really sort of implies that my data that I have is really glued to that application that it's co-resident with. On my replicated data grid model, I can basically use my data grid for multiple applications, right? Because it's basically disconnected off on another data tier, if you will. And then same thing too from the sharded perspective, right? So once I start going to that decoupled model, there could be opportunities to be able to get more value out of that data, right? Because it's not so tightly coupled to the application.
So I think what I like to do now is take this and start scoreboarding it and look at the good, the bad, the ugly, and some of the realities we deal with. So the simple one to look at is responsiveness. Start there. You have the option of a fully replicated embedded model. So one application, fully replicated, availability, all that. But it's embedded to one application and has these limitations. It is fast. It is much faster because anything you read is already there. Anything you write asynchronously will in the background update other things. Only synchronous writes are things that you wait for. In the other models where you separate a data tier, so it's never in your application, you talk to something else, any operation you do against that data is a cross-process, cross-network operation. So obviously speed is better when you're embedded. However, that's the good. The bad part is data size limits. And in the data size limit, unfortunately, we score very poorly on the embedded replicated and even on the data grid replicated models because the amount of data we could practically handle and keep within one instance of an application is limited by the amount of data we're willing to keep in one process. And in the Java world, that amount of data is not very big, and we'll get to that. The unlimited amount of data that you get from sharding is very, very attractive. You can hold gigabytes or terabytes of data, or even more, petabytes of data, across a well-sharded data grid that scales horizontally very well. The minute you've decided to shard the space and create a separate data tier and take the hit of leaving your process to get to it, you get ultimate scaling in data. So that's a very, very attractive model. People move to it often for two reasons. The first one is scaling the data. The other one is separating it as a shared environment. If we look at the shared thing, the being tied to application versus not being tied to the application, there is a key difference there. But it's not really something we can score as red or green or yellow because it kind of depends on what you need. In my experience, and I think when we talked, you indicated the same, the vast majority of applications that we meet that use a cache or a data grid tend to use that data grid in a completely application local way. It is architecturally already tied to the application, and you don't find a lot of sharing between applications and the data grid in those architectures. I'd say in my experience that's about 80%, 80+% of actual deployments of data grids. So in the other cases where the data grid is truly an independent tier, has a separate life cycle and so on, that sharing is very valuable. The sharing alone will drive you there. That's the architecture. But when you're looking at the data grid as an application internal concern of a way to manage, say, product catalogs or streaming events from things, often it's an application local concern, in which case there would have been an option to use the faster path, except for the limitation of process size. And that limitation is very strong. The limitation really comes from what we call hiccups. And the fact that as process size grows, so do the hiccups and the stalls and the jitters and the freezes in your process. And there's a practical level to how much you're okay, how big of a freeze you're okay having a process having. And when that gets to the pain you can't take, you stop growing the one process. That means that the size of data in a data grid in the left-hand sections is limited by the size of hiccup you're willing to take. The good news on the right side is it's not limited by that. Over there, you can always shard very thinly, and if you want, you can create shards with only a few megabytes in them or tens of megabytes. My experience is usually a shard is a few hundred megabytes of data and a gigabyte or two a heap, because that freeze is painful, but not too painful for most data grids. The same applies on the left. You typically only take those to a few hundred megabytes before you're forced into a separate tier and a separate sharding for scale. So what do hiccups look like in a Java application? Let me give you a visual that's plotted for hiccups. This is a plot of discontinuities in execution of a JVM when it's actually running a Java workload. On the top, you have sort of the, over time, when you have hiccups, when there was a stall in the application for some reason or another. At the bottom, you have a depiction of that as a percentile level. So for any percentile, you ask, like, okay, the 99 percentile, how bad is it? And you'll get a number there of, in that scenario, the 99 percentile would have experienced a hiccup of at least this big. This is a good depiction of, and a good way to think about the platform itself, not your application, but the thing that runs your application, and whether or not it was able to run all the time. We often work under the assumption that computers run continuously, but they don't. We can measure if they do or don't. So, where do I get this kind of thing from? There's a tool called JHiccup. I actually built it about 3 and some years ago. And there are all kinds of reasons I built it, but it's being used a lot to study the actual hiccup behavior of applications. It's meant to basically capture the hiccup behavior of your application on your JVM, on your computer, on your operating system, on your hypervisor, on your hardware, and anything in the middle. And it's simply an observation tool. It records any observed discontinuity of execution, and it does that in fairly fine resolution every millisecond, so that anything that freezes for more than a few milliseconds is impossible to hide from it. And then you just get a nice report that tells you, what happened in a chart like that. It's very easy to add to any Java application. You can just add it as a Java agent to the command line. There's also a nice wrapper script. You can even attach to a background thread if you want to. And all it does is add a sampling thread that collects 1,000 times a second. Basically, it tries to wake up 1,000 times a second, and anytime it couldn't wake up in time, it reports, oh, there was a hiccup of this length. It's very cheap, very low in cost. It's also very, very open source. So this is public domain code. It's up on GitHub. You could take it, integrate the concepts into whatever you want, but there's also a nice wrapped Java agent you could just use directly. This thing is about 600 lines of code, so there isn't that much complexity to it. Now, one of the common uses, or some of the common uses of this, have to do with looking and logging at production time or performance time characterization of systems. So often you just add this thing, it logs hiccups, and then you can reconstruct a window with the picture I just showed you before for any point in time. You could say, hey, yesterday between 8 and 9 a.m. there was weird behavior. What was my hiccup? What were my hiccups looking like? To give you a good example of how that's being used today in production, It's very useful for isolating and triaging problems. Suppose you have an actual glitch in your behavior. Something went wrong. Something's going wrong. You can go back and look at the logs for hiccups and isolate things. So you can have a hiccup log for your JVM. You can actually have a control hiccup very easily that runs an idle workload on the same system at the same time. And from those two hiccup logs, again, you can isolate a lot of problems. It won't tell you where the problem is, but it certainly will tell you where it isn't. For example, suppose we had a glitch in operations. A data grid was failing to respond for a couple of seconds. Something went wrong, and then it went back again. It works now, but we're trying to figure out how to make it better. You go back to your hiccup logs, and if your JVM hiccup had a glitch at the same time, and your control mode hiccup had a glitch at the same time, that tells you that your system glitched. Anything on that system just couldn't run for a couple of seconds. Your problem is not your code. Your problem is not your network. Your problem is not your JVM. It's probably the operating system or something below it, because on that operating system, anything trying to run couldn't for 2 seconds. That's good isolation. You don't have to check a bunch of things. However, if your hiccup logs show that the system was happy, the idle control thing didn't see any glitches, but your JVM saw a glitch, now you know that it's not your code, not your network, but also not your operating system, hardware, hypervisor, and the rest. It's your JVM. So go look at why your JVM is experiencing a hiccup. That's where we often focus. And then the last one is, hey, maybe they're both happy. Yeah, you had a glitch, but neither the system or the JVM experienced one. So it's not the system, not the JVM. Go look at your code, go look at your network, figure out what's going on there. That's a three-way triage, and it's very useful. So digging a little out of the tool itself and looking at examples of how we often see it used, and we use it a lot in trying to figure out the smoothness of large systems, you can use it to start with to just make sure your system's running cleanly. We often have people tell us, hey, we have a data grid deployment we want to do, and we need it to answer in 10 milliseconds in the worst case. I never want to see longer than 10 milliseconds. I don't want to see any of those big flips going around. I don't want to time out at 50 or 100 milliseconds, so I need it to be smooth. The first thing I usually ask people to do is run an idle JHiccup on the system with no load at all to see how much their system on its own is glitching. And I will often see something like that. That system glitches a few times an hour to 20 milliseconds. At that point, I know I don't need to do a test because that system's going to fail the test. If it's doing it at idle, nothing I can run on it will do better. The good news about that is you can clean a system with several different things you can look up online and get Linux to behave fairly consistently. Glitches of no more than about half a millisecond or maybe a millisecond over periods of hours at a time. It's very good for making sure that you have a clean system before you start trying to get it to do things that it can't do because it naturally has noise. Now, beyond looking at noise on a system, you can compare behavior of different application settings, different collectors, different JVMs. For example, here we're comparing the parallel garbage collector to the G1 garbage collector on exactly the same workload. This is a 1 gigabyte cache held in an 8 gigabyte heap under a load generator for that cache, and we have different behaviors. Either good, bad, just look at them and compare them and see which one you want or what you want to tweak. It's a good way to look at it pictorially. These are the hiccups that happen when you run and different settings for them. Now, obviously, I had a reason when I built it. And this is an honest description of the reason I built JHiccup. Charles Nutter is the JRuby guy. He works for Red Hat for the last couple of years, I think. But this is an honest description of what the tool is good for from Azul's point of view. We use it to show how our JVM is better. Because if you look at hiccups, you can then compare them. So for example, on the left, we have regular hotspot with a well-tuned CMS running that 1 gigabyte cache, an 8 gigabyte server. And on the right, we have Zing doing exactly the same thing. Can you see how much more beautiful the hiccups for Zing are? I mean, look at those spikes and look at that line, right? Well, they both have spikes and they both have a curve. But let me highlight the scale. And I don't know if you guys could see the numbers from back there, but let me normalize it now. So they're to the same scale. I don't show this as the first thing because people complain that there's no data on the right. And it's really hard to show that you're 1,000 times better on hiccup levels when you only have 500 pixels. So yeah, bragging, a lot of bragging. But this is what we mean by hiccup-free Java. You can get Java to do that. And you could get Java to do that any amount of memory that you can put on a machine. And that's the really good news. because that means you could change the way you do your duct tape engineering. So in a hiccup-free Java environment, you could take out all of GC as a concern, right? The glitches become less than OS and hardware and hypervisor noise. And then whether they're large, small, they're gone. And you can apply this to anything from low latency messaging and data grids and human response to them, or even big analytic applications. Large heaps, small heaps across the board, the glitches in the GC are gone. It's just a solved problem, and you no longer have to tune it. Now, what it also means is that you don't need to engineer around those things anymore. You don't have to architect around them, and you don't need the duct tape that has to do with them anymore. So the various duct tape behaviors we often see that deal with the small process size incurred by large hiccups are gone. And that means simplified architecture. Now, if we go back to this scoreboard and look at where we had our strongest limitation to deployment, what pushes us to highly sharded architectures that can handle petabytes of data, but what pushes us there early? It's the single process size limitation. In practical terms today, one process in Java, if you want a data tier that reacts well, meaning you're not going to have seconds of delay every once in a while, you're probably going to keep only a few hundred megabytes of data in one process because it'll glitch larger than you're willing to accept otherwise. By eliminating the glitch, we move that one process size from being limited by hiccup size to being limited by hardware size. And luckily today, hardware is pretty good. So we can take out that as a limitation. It becomes a choice. And now you could choose which one of these architectures you want to deploy. Now, don't get me wrong. If you need large amounts of data, larger than would fit in a machine, you absolutely should use a sharded, separate data tier model because you can grow it infinitely. Well, infinitely. However, if your data is tiny enough to fit in one machine, remember, not in one process that you're willing to hiccup, but one machine today, you have the choice of using the other modes of data grid deployments and getting the benefits of speed that come with them. Local reads, local async writes, only doing delays that are cross-process when you do synchronous operations. And those are pretty big things because they could translate to 100x differences in sustainable speed out of the exact same data grid software. So when you look at Zing and data grids, we dramatically improved the service levels because even on the distributed ones, you can go for tighter service levels without sort of cascading failovers to work around glitches. But we changed the practical one process size by a little bit, from a few hundred megabytes to a few hundred gigabytes. And yeah, that's 1000x. It's a huge difference in what you can practically do with a fast replicated data grid today. Now, fully replicated and embedded is now practical for the applications where that's an architectural match, where moving to the sharded model was a duct tape form of moving the stuff away within the same exact APIs. And whether you're running a gigabyte or 10 or 100 or all the way to terabytes, it's practical in one machine, commodity today. There's no extra tax for that. You could go to Amazon, get a 240 gigabyte heap right now for about $2.80 an hour. So these are practical things that are not hard to get. Show you that on Jboss Datagrid and the actual effect. This is a simple way to view it. Jboss Datagrid is great. It scales very, very well in instances, across instances, and it can handle large amounts of data, whether it's in process or in across processes. However, when it's running on JVMs that glitch and hiccup, it's forced into a highly sharded model early, before it has to. And you can see that as the size of the heap grows up, this is a 10 gigabyte heap, a 40 gigabyte, a 50, 100, the percentiles and the hiccups that you take become much larger. What Zing basically does is flatten that line regardless of data size. The worst hiccup we saw in a system running a 200 gigabyte data grid heap in one process, fully replicated, was 23 milliseconds, which is a little bit better than the many seconds cases that are just not acceptable in others. So with that, I'm going to switch over to John, who's going to talk about some of the examples of using data grids in the practical world.
Right. So in order to tie all this together, it's interesting, how did we get to talking about data grid and how does this all fit? So one of the key things is looking at streaming telemetry. So what I mean by this is, and this is an architectural paradigm that repeats in a lot of scenarios. So let me show you what this is. It's really based on something where you have distributed sensors, okay? So I have something reading the environment, and then I have something that wants to respond to some kind of correlation of what's happening in the environment and actuate something. So I want to have some kind of process control. It's built on an event response type model, right? So I've got the sensors kicking off events, and then I want to generate some response to not only maybe that one sensor event, but the understanding and knowledge of what's all happening across the whole sensor network. So then I want to be able to generate these events, collate these events in some way that I can compute across them. I can analyze them. I want to have some kind of intelligent processing and then react. So where this shows up is in a lot of different vertical industries, right? So you can think of manufacturing, right? You could think of a production line. You could think of the robots. You could think of sensors seeing as parts are moving down the conveyor belts. You can think about transportation, right? So talk to a lot of the airlines, right? So all the way from moving passengers from the minute you say you go online, you consider buying a ticket, you buy the ticket, you show up at the airport, you go through the TSA screening, you arrive at the gate, they've got to coordinate where the planes are, where your baggage is. So again, you'll have sensors, you'll have things that respond to them. Even into things like shipping, right? So you can kind of think of maybe a railroad, right? So a railroad maybe wants to understand where the position of train cars and engines, and because they've all got basically a single track that these things need to coordinate across, right? So I've got to maybe do switching. I've got to know where the trains are, how fast they're going when I throw the switches, et cetera. Even into oil and gas and petrochemical companies, right? I've got refineries. I've got oil exploration. I've got even distribution out to the retail side of oil and gas, right? So the gas stations. So lots of places where this applies. And if you look at kind of what are the requirements for it, so I want to, a lot of people that have these things, they want sort of a real time, and I'll kind of throw a real time around, but they want to be able to kind of understand what's all happening in that environment through some type of dashboard. And really what's important is that these events that are kicking off, I got to be able to process them consistently, right? I can't have the pausing and the stopping that I traditionally have in Java. Java's fantastic for all of the different frameworks we have, all of the different libraries. It makes it really easy to develop software. A lot of people know it. But when it starts becoming non-deterministic, that's when it makes it hard to maybe apply to some of these applications. And that was really what drove this scenario. So what did this look like? So this is based off of a real-world example of something that we put together. So we have, this is kind of showing an oil and gas type of environment. So we have the core drilling on the left-hand side. We basically have some intermediate storage and management of, say the raw materials being shipped and transported then to the refinery. And in each one of those steps, we have a set of sensors and then different things that actuate based on what's happening. So what the customer wanted to do is they wanted to have this big overall end-to-end view because the way this worked in the past was they'd send field people out with a little notebook, and we'd take notes, and then they'd basically ship them back home, and after a month they could correlate all this stuff and start making decisions about how this all was moving. So the whole idea was automation, right? So it comes down to this whole Internet of Things. So what are the things? The things were all the things in this process. And what they wanted to do then was orchestrate them across more or less the whole organization. So we put in a messaging bus, right? So this is based on the Fuse technology, and we actually used the Azul Zing JVM there as well because we wanted to make sure that we weren't impacting any of this whole processing with any type of, the pausing and the hiccuping that he talked about. And then really what was key was a set of applications. So you see on the left-hand side here on the top, they built applications. So these applications were basically then taking these events that were being propagated into a set of topics, right? So they were published to these topics. And then we also more or less maintained all of this information in a data grid. So that's where this data grid's coming into play. So, not only did I have sort of the real-time process control, but I wanted to sort of have a historical view of everything that happened, because what they do is they would actually run traditional, what we call today, big data analytical processes over these things, right? So, how many of you guys have heard of Hadoop? Does everybody know what Hadoop is? All right, good. So, if you know Hadoop is sort of a batch process, right? So, Hadoop is sort of an evolution of the extract, transform, and load, and I've got, it's more of a downstream batch process. What they wanted here was something that was much more real time. So, I didn't want 20 days of delay to what I was looking at. I wanted this real-time dashboard. So that's one of the things that they can do with Datagrid is you can actually do map and reduce type workloads in this whole space of all the event information that had been collected, throughout this whole process. So, not only, so they got two values out of this architecture and this solution. The one value was that they actually now have automated this thing, but now they have a whole set of data that they can really begin to understand over a period of time how everything actually fits and works together. So it was not only just operating day-to-day business, but now I have a whole set of intelligence that I've kind of done through this big data.
I think one of the, and we're kind of not talking about the who exactly.
Right.
Again, but one of the values is taking that amount of data, that window into what's going on, analyzing it, but then closing the loop to actual action. And when you close the loop to actual action, it's amazing how quickly people roll from closing the loop means the CEO knows things, to closing the loop means a lot of people know things, to closing the loop meaning, oh, we actually do something about those things manually because we could see that a minute ago something happened, to we now write robots to look at the data and react to it. And that's where the loop really closes quickly. Maybe you want to move a valve. Maybe you want to shut something off. Those start being a reaction to the data, and that's where the real-time aspect of it, more of a business real-time. Fast enough for whatever operation you have is important. But fast enough for whatever operation you have is becoming very quickly a sub-second kind of thing from a consistency point of view. And now you're looking at things where batch operations and something that freeze for a minute at a time is just not acceptable. So you have to build it on something that will scale and deliver the consistency and reactiveness.
Yeah, so give you all another example. So this is a case of fraud detection. So to kind of walk through it, the idea is that I have a distributed set of card scanners and terminals, right? You walk up, you run your card through, something's validating you. Again, it's an event response driven thing. So we generate the events, collate them, analyze, process, and in this case, you want to sort of come back with an approve or deny. So what's really important here, who likes when they go shopping and you swipe your credit card and you're waiting and you're looking at the terminal and you're waiting to see, right? Anybody ever experienced this where you're just kind of standing there and you're wondering if your credit card's going to be denied or what's going to happen, right? And so people want this to happen fast. People don't even want to wait for this anymore, right? So how quickly you can get that back, right? That's really, really key. So vertical industries, retail. Retail is a big one, right? Healthcare. So, basically validating, your health insurance. Finance, right? So you go to your bank, you're basically, have your ATM card, what have you. Small and medium businesses, right? So this is big with them. Even into large enterprises, a lot of stuff around credit processing, right? So the requirements, what you'll see here, this is, I want it to happen in near real time, but now I'm talking about massive scalability, right? Because now I want to understand maybe what's happening nationwide, right? That's a key thing they look for, right? Is, oh, you just used your credit card in Los Angeles, and then 2 seconds later it got used in New York. How in the heck did that happen, right? So you got to start being able to correlate all these events and have do that quickly, right? So because the quicker you can identify sort of these fraud cases, you can do something about it. So, again, you want a very consistent approach. You don't want to have any really big outliers that could cause the system to hang for a long period of time, because it's all about the customer experience, right? That's key. And customer experience also really includes security, right? Nobody wants to have their information stolen, and then also efficiency. So, what does this look like? And you'll see there's sort of a lot of overlap in parallelization with this one as well. So, that was kind of the interesting thing as you begin to delve into this. What can I do from a Internet of Things kind of real-time collection of remote information? I have the same kind of thing recurring, the same theme, right? I need to have some kind of messaging bus that's routing this information. I basically have some type of process, but then I start want to collecting all of this information so that I can begin to perform my analysis and analytics over the top of it, right? So pretty much the same thing, but what was key here, what you'll see is that's different, is I now have the ability to scale this up. I have total horizontal scalability. I can add more devices, more industries at the bottom. And then as I need more processing power from the credit validation tier you see in the middle there, I can just keep adding more instances of that, because that's really being enabled by my messaging bus that's routing and collecting information. And then, again, I also have the same data tier. But what's also interesting here, you'll see, is that there's actually now a persistence layer. So I want to, in this scenario, this information, I also want to have persisted, right? So it's not maybe just a temporally spurious piece of information like we had in the process control model. There maybe wasn't so much interest to, say, persist this. In this case, you may want to have a hard written record of, all of somebody's credit transactions, for example.
It happen every time money is involved.
Yeah, every time, yeah. So that's another cool thing you can do with this, right, is you let all of the high volume information go through this in-memory cache and Datagrid coming off of your sensors and your application processes, and you're letting the Datagrid, again, remember what the Datagrid was? It was sort of a framework, right? The Datagrid then is actually handing all the persistence off to that spinning platter of Rust. So I didn't have to change my application at all to basically enable the ability then to persist this off to a disk.
We actually, this is a good example that's specific, but I think we're seeing a pattern of a lot of this being deployed, this combination of a fraud detection need on top of a lot of messages volume going in, being cached in some sort of a window of time that you do your operations of fraud detection on, and then persisted to the side. We're seeing this across everything. Another vertical is just online services, large online services that can't handle fraud as logins and misuse of that kind of stuff as well. And this is actually one of those places where the speed of the in-memory cache becomes critical, because the window of time you can actually handle and process is often limited by both what you can process across it, how fast you can look in it, ask questions of it and such, and also by what sort of SLA you're willing to take on it. So, if there is somebody waiting, often the budget to make a risk or a fraud detection on a credit card swipe is counted in tens of milliseconds. If you don't make a decision in 20 or 50 milliseconds, you need to either deny or accept without knowing. And that's becoming more and more of a problem, because the cost of fraud, at least in the US, has tripled in the last few years. So, it's a very costly thing to let an operation through without checking. Therefore, there's an SLA, there's a time you have to finish it in. And you have growing amounts of data you want to process. So you have a need for high throughput, very fast reads, but also keep it consistent from a time perspective. This is where the amount of data you can hold in a heap becomes critical, because we're seeing situations where those caches are being used in that fully replicated, laterally scalable processing mode, but where the data is actually in all the caches everywhere, so that everything is very, very fast to read. So that rather than your operations being kind of a collation of a lot of cross-process thing coming in, every read becomes a cross-network latency. They become about 50 to 100 times faster when they're all local. And again, the size here, the ability to have a window of hundreds of gigabytes of data streaming through for the last hour of operations of an entire organization, for example, becomes critical.
Yeah, and then if I can also add too in this one, so not only was the Datagrid enabled with the JVM, but then also we had the Jboss Business Rules Management System. You'll see that up there. So the business rules was actually also enabled with the JVM as well as the Fuse and AMQ messaging bus. So the whole idea was to eliminate any type of pausing that would affect how quickly I could process any of this stuff through my traditional Java middleware.
I think just looking at the time, we've got 10 minutes to go. We can run quickly through the last use case and then jump into summary and Q&A because I'd really like to hear questions.
Yep. All right, so we'll go quickly through the last one. So the last one was an e-commerce case. The idea was to be able to take an environment that existed, right? So it wasn't a greenfield. It was like, how can I take an environment that already exists and enable things? So again, it was the events or people checking out, right? Checking out could be I'm at the cash register and I'm scanning my items, or checking out could be that I'm on a mobile device or I'm doing web commerce, the whole omni-channel. Again, same kind of needs, right? Because the quicker I can get the customer out of the store, the happier they are. They don't want to stand in line, the whole thing. So again, you'll see very similar things here. I don't talk too much about Datagrid because we talked about that quite a bit. This is really to look about rules processing. And what was kind of really interesting with this and where the Zing platform came into play was actually in an embedded JVM that was actually running inside the point of sale controller. So we were able to actually get the BRMS runtime engine actually running in an embedded point of sale controller, so that they could basically now not only have the same type of business rules running on their mobile devices and on the web checkout, but also have it in your traditional checkout lines as well. And you'll say, well, why is that interesting? Well, because when you look at what retailers want to do, they want to reward their most frequent customers and really start to understand what their customers are doing, right? So what better way to do it than to really start understanding through rules what you're purchasing at the store, what you're purchasing online, and what you're purchasing on mobile. They can begin to start offering a very customized and personalized experience. And so, that's where this became interesting is they were able to sort of readapt that legacy point of sale system and bring it into the modern world and have it all consistent across the multiple omni-channels.
To give you a practical example of rules at checkout, because often people have okay, what does that mean? Fraud, I understand. Think of what it means when you say, buy two, get one free. And the two is not the exact same thing, but buy two of any of those, you get one of any of those free. There has to be processing at the point of checkout that actually finds that you bought three in the group and you're supposed to get one of them free, right? Because nothing else will do it. And it's personalized and it's at checkout time when you move it out. So these are examples where you end up with rules and rules and rules. And this is a very simple example to get much more complex, where you have to run full rule engine processing on each checkout transaction. It's not an occasional sample. And if people don't get the actual promise of buy two, get one free, they get very upset when the bill's wrong. So it's not something you could do sometimes. It's not something you can give up on. It's not something you can afford to take risk that maybe the fraud isn't happening. This is a transaction you're supposed to get right. And you have to go through all the rules of whatever it is you did. Unfortunately, for us in IT, you give marketing people and process people the ability to express those interesting rules on what happens during checkout, you don't have just two rules to deal with. They keep adding and adding and adding. The complexity of them grows, and therefore the performance of being able to do them is critical. Okay, so I think we'll quickly summarize and then take some questions. So we talked about the duct tape and the in-memory and the data grids and all those. A simple summary to look at Zing is that Zing enables on-heap computing. Off-heap computing is a really good example of duct tape engineering, but off-heap computing is so 2010. We're 5 years later here. And yes, you will see a lot of very useful, very heroic examples of people taking off-heap engineering and applying it to a common piece of infrastructure. And every time you see one of those, think of the 2 years of wasted engineering of all the people that did that and didn't do something else because they had to work around a problem. That problem is gone. The need is gone. Off heap is not needed if you run on a heap that doesn't stop. On heap is faster. There are no more pauses, and on heap is always faster. It's always cleaner. It always removes complexity from the system. And it has only one drawback. If you run on a JVM that doesn't like a lot of on-heap material, you have a problem. You need duct tape to work around. Similarly, if we look at the duct tape effects, in-memory data grids, and specifically the Jboss Datagrid that we have a lot of experience with, are a really good example of using on-heap architectures for speed, for simplicity, for delivery, and we gave you some good use case examples. You have a single model for dealing with your data. You program in one way, and then you can deploy it in any of the options we talked about. There's no one right way to do it. There are variations of ways, and you have choices. And those choices often trade off size, geographic distribution, and speed. And the right choice is really a question of your application deployment, but it doesn't have to be a question of application architecture. So you don't have to roll your own, cross-process anything. That duct tape is gone. There are multiple good data grids out there, but Jboss Datagrid is a really good example of one that makes the right choices on simplicity. It did not invest in a lot of engineering to work around the solved problem, and instead it invested in engineering in getting a high-quality data grid that works across a lot of good use cases. So with that, we'd like to take some questions and see what people would like to know about any of the stuff we talked about so far.